Astronomers using the James Webb Space Telescope have reported an extraordinary discovery that pushes the boundaries of how far humanity can observe the early universe. A powerful gamma-ray burst detected in March, now known as GRB 250314A, appears to have been produced by the explosion of a massive star just 730 million years after the Big Bang. This finding suggests that some of the universe's first generations of stars were already living fast, dying young, and producing the most violent explosions known. The event may represent the most distant supernova ever observed, occurring in a faint, barely detectable host galaxy that existed when the cosmos was still in its infancy. Such a discovery not only adds another milestone to JWST's rapidly growing legacy, but also provides a rare window into how stars and galaxies evolved during the earliest chapters of cosmic history. Gamma-ray bursts are among the most energetic phenomena in the universe, capable of releasing more energy in a few seconds than the sun will emit over its entire lifetime. They appear suddenly, shine intensely, and vanish almost as quickly as they arrive. Because of their extreme brightness, gamma-ray bursts can be detected across enormous cosmic distances, making them powerful tools for probing the distant universe. GRB 250314A was first identified by the Space Variable Objects Monitor, a compact X-ray telescope developed through a collaboration between China and France. This international partnership enabled rapid detection and localization of the burst, triggering a worldwide effort to observe its fading afterglow across multiple wavelengths. Within days of the initial alert, astronomers realized that GRB 250314A originated from an exceptionally distant source. Measurements indicated that the light from this explosion had been traveling for more than 13 billion years before reaching Earth, meaning the event occurred when the universe was only about 5% of its current age. At such an early time, galaxies were small, faint, and still assembling, and heavy elements were only beginning to form. Observing a gamma-ray burst from this epoch is therefore extremely rare, as only a handful of such events have ever been detected within the first billion years after the Big Bang. This rarity is precisely what makes GRB 250314A so valuable to scientists. Early universe gamma-ray bursts offer direct clues about the lives and deaths of the first massive stars, which played a crucial role in shaping the cosmos. These stars forged the first heavy elements, reionized the surrounding hydrogen gas, and influenced how early galaxies grew and evolved. By studying the properties of the burst and its afterglow, astronomers can infer the physical conditions that existed in the young universe, including the chemical composition of early stars and the environments in which they formed. Two independent research teams analyzed GRB 250314A using data from JWST and other observatories, and both reached a striking conclusion. The characteristics of the burst strongly suggest that it was produced by the collapse and explosion of a massive star, rather than by the merger of compact objects, such as neutron stars. This distinction is important because gamma-ray bursts are divided into two broad categories. Short-duration bursts, lasting less than 2 seconds, are thought to arise from the collision of neutron stars or a neutron star and a black hole. Long-duration bursts, which last several seconds or more, are associated with the deaths of massive stars that collapse under their own gravity. The initial flash from GRB 250314 lasted approximately 10 seconds, placing it firmly in the long-duration category. This duration immediately hinted at a stellar collapse origin, but duration alone is not enough to confirm such a conclusion. Astronomers therefore turned their attention to the afterglow, the fading emission that follows the initial burst. Although the gamma-ray flash itself is brief, the afterglow can persist for days or even weeks, emitting light across the electromagnetic spectrum, including X-rays, visible light, radio waves, and infrared radiation. It is within this afterglow that the richest scientific information is often found. JWST's unparalleled sensitivity in the infrared made it uniquely suited to study the afterglow of GRB 250314A. Because light from the early universe is stretched to longer wavelengths, as the universe expands, infrared observations are essential for detecting distant objects. Using JWST, researchers identified a subtle but telling excess of light that is consistent with a supernova emerging beneath the fading afterglow. This signal matched theoretical predictions for what a supernova associated with a gamma-ray burst should look like at such extreme distances, providing strong evidence that an exploding star was indeed responsible. A.J. Levon, lead author of one of the studies and a professor at Radboud University in the Netherlands and the University of Warwick in the United Kingdom, expressed astonishment at how closely the observations matched prior predictions. The successful detection demonstrated that JWST is capable of observing individual stellar explosions at distances once thought to be completely inaccessible. This achievement marks a major step forward for observational cosmology, showing that astronomers can now directly study the deaths of stars from the universe's earliest eras rather than relying solely on indirect evidence. Both studies describing these findings were published on December 9th in the journal Astronomy and Astrophysics, underscoring the importance of the discovery to the scientific community. Together, they paint a picture of a young universe that was already surprisingly active and complex. Massive stars were forming, evolving, and exploding, enriching their surroundings with heavier elements and influencing the growth of early galaxies. The faint host galaxy of GRB 250314a, barely visible even to JWST, serves as a reminder that much of the early universe remains hidden, waiting to be revealed by powerful new instruments. Beyond setting potential distance records, the discovery has broader implications for understanding cosmic evolution. If massive stars capable of producing long gamma-ray bursts were already common just 730 million years after the Big Bang, this suggests that star formation in the early universe was highly efficient. It also implies that the processes leading to stellar collapse and black hole formation were established very early on. Such insights help refine theoretical models of how the first generations of stars differed from those forming today. GRB 250314a also highlights the importance of rapid, coordinated observations in modern astronomy. Detecting a gamma-ray burst is only the first step. Extracting its full scientific value requires swift follow-up observations across multiple wavelengths. The success of this effort demonstrates how international collaboration and advanced technology can work together to unlock the secrets of the distant universe. As JWST continues its mission, astronomers expect that more such discoveries will follow, each one shedding new light on the origins of stars, galaxies, and the complex cosmic web that surrounds us. With every distant explosion captured, humanity moves closer to understanding how the universe transformed from a simple, primordial state into the richly structured cosmos we observe today. The detection also raises intriguing questions about the nature of the stars responsible for such explosions in the early universe. Many astronomers suspect that some of the first massive stars were significantly different from those seen today, possibly larger, hotter, and composed almost entirely of hydrogen and helium. These primordial stars, sometimes referred to as population 3 stars, would have lived short, violent lives and may have ended in spectacular explosions capable of producing powerful gamma-ray bursts. While it remains uncertain whether GRB 250314a originated from such an ancient stellar population or from a slightly later generation enriched by earlier supernovae, the event provides a crucial observational anchor for testing these ideas. Equally important is what this discovery reveals about the environments in which early stars formed. The faintness of the host galaxy suggests that even small, low-mass galaxies were capable of producing massive stars and extreme explosions. This challenges some assumptions that only larger, more evolved galaxies could host such events. Instead, it appears that star formation and stellar death were already widespread and dynamic across the early universe. Each explosion would have injected energy and newly formed elements into its surroundings, influencing future generations of stars and gradually transforming simple primordial gas into more complex cosmic structures. Looking ahead, astronomers anticipate that GRB 250314a is only a preview of what is to come. As detection methods improve and JWST continues to survey the sky, more distant gamma ray bursts and associated supernovae